Okay, I'm Charles Bowman, and this is ECE641, and we've model-based image and signal processing. It's really model-based image processing, and I call fall 2020 the pandemic edition. Okay, but the oh my glasses are fogging up. Alejandra, can you just check to see when I talk, are those little bars bouncing up and down? Because that would indicate that it's recording my voice.
It is.
Okay, good. Oh yeah, so they felt there wasn't enough going on this semester. It was getting a little boring. So they decided to not just like go to quasi-hybrid educational model, but to also switch it from Blackboard to Brightspace. And I haven't done anything with Brightspace other than merge the 4 sections of my class. Oh, I should start off by saying there's 4 sections of this class. I didn't make that up, okay? So hopefully that's not causing confusion. I don't really care which section you sign up for. It's pretty much the same, except for one thing, and honestly, it's almost moot for sure, which is, in theory, if the room filled up with 35 people, then if you didn't sign up for the first version, which is the 641 or 0001, you wouldn't have a spot reserved for you in the room, okay? But obviously, the room's not full, okay? So. And it's not going to be, I don't think. So it really doesn't matter which section you sign up for. It might matter to you, because some of the sections you may have to pay money for or something like that. I don't really know, okay? So sign up for whatever section you want. And if you want to take, obviously I'm going to be posting, first of all, there are videos on online for this class anyway, on YouTube, which I'll show you in a minute. And I'm also going to be recording the class live, okay? So that you kind of get the experience and that people get the fresher take, okay? And then the exams I haven't exactly figured out, and actually the stuff I put online as far as course, I didn't even bother updating the course roster because it occurred to me that everything's up in the air. Like I think it's, again, correct me if I'm wrong, okay? But my understanding is that the Board of Trustees has already decided we're not having classes after Thanksgiving, right? Okay, yeah, but we will continue. Okay, I don't want to like frighten anybody, but I think we all well, okay, my understanding and my intent would be we'd continue after Thanksgiving. We just do it on Zoom, okay? So, because there's, otherwise we really couldn't get through the course material. And and let's face it, Notre Dame, you know what they said, there's like, it's really kind of fun. You can go to the COVID-19 dashboards at all the different universities. It's like they set up on Reddit an August Madness webpage, an elimination to see who's the first to like cancel all their classes and go to all fully online. So I'm doing my part by showing up in class to try to help spread the virus. No, I'm sorry, I didn't mean that. That was just a kidding. That was a joke. Don't tell Daniels I said that. Yeah, so who knows, right? I mean, but life is uncertain. One thing, just to venture into philosophical a little bit, a friend of mine mentioned that, a lot of times during times of dramatic change and so forth, sort of uncertainty, a lot of good things happen sometimes, because what happens is everything's kind of thrown about, and people aren't watching so closely, and people do interesting, innovative things that otherwise they might not be allowed to do, or whatever, I don't know. So maybe something good will come out of this. We'll look at it back in 10 years and we'll think, gee, that was kind of interesting, So, so you got to take the good with the bad. But in any case, so I thought I did ask for this larger classroom, because I thought it would be really good to have, I had a feeling very few classes would be running in person, okay? And it's got to be really boring out there just watching videos in your room. So I think it's kind of nice if we can actually get together and have some conversation. And here's a plus. It's a small class, so we can be more conversational, okay? And also, I was actually thinking of, instead of having exams, maybe trying to do projects this semester or something like that. I don't know. Playing it by ear a little bit, okay? So, I mean, because let's face it, everything's kind of up in the air. But if we do have exams, and I'm not saying we won't, because I think that there's some value to it. We'll probably use GradeScope, which means I think if I can bypass Brightspace, I will, because I really don't feel like dealing with it. But I think maybe you have to use Brightspace to use GradeScope. How many people have taken exams with GradeScope? The biggest, how did you like it? It was okay? The biggest hassle, well, not hassle, but the biggest, I liked it as an instructor, but it's a little more trouble to prepare the exams, but it's much easier to grade them. But the biggest problem from my perspective was that some students had difficulty adapting to how you have to interact with it. You have to scan your exams and upload them, which confused some students. But maybe once you get used to it, I think it's not so bad. So maybe we'll do something like that. Maybe we'll do I put down some percentages for exams, but maybe I'll adapt those, okay? Basically on how things go, and I'll reinterpret them, okay? And we'll do some project or something like that. I can't see, my glasses are all fogging up. It's really humid in here. I'm gonna have to get better masks. Why didn't Purdue provide better masks, okay? There's something they could do. Excuse me?
They went for the fashion.
They went for the fashion. Did they actually give you, does that say Purdue on it?
Yeah.
Can you get those somewhere?
You can get them from the graduate center.
From the where?
The graduate office, graduate student office.
Oh, really? You're kidding.
I'm afraid for staff.
I thought that they were supposed to be put, okay, that's what I thought I was going to get. I'll go see if I can find it later. Thanks for the info. So 641, so Brightspace, I won't be using that much. Did that cause any confusion for people? No, okay, you guys don't care, right? Okay, I was just checking. If you listen to the administration, you'd think that like the world comes in and if you don't use stuff like that. And, I just have my own web page. I put on there what I think we need to learn, okay? What is this course about, okay? I'm going to talk about that in a little bit, but this course is really about solving, okay, this course really is about the underlying tools used in computational imaging. Have people heard of computational imaging? Okay, that's like a thing. I'd just like to say, okay, you can say I'm full of crap, but I'm not, okay? I invented that name, okay? I did, okay? I created a conference about 20 years ago. Then I kind of popularized it subliminally. I used my mind control powers, okay? And I started a journal on computational imaging, and now it's really started to become a thing. So that's sort of fun. But I wouldn't say this is a course on computational imaging, because I was thinking to myself, why didn't I just name the course computational imaging? It's really not computational imaging in the following sense, that if your computational imaging is about the various kinds of sensors, computational imaging is really about bringing computation together with sensors to solve imaging problems, to construct images. You know, this is kind of an abstract idea, and people are just beginning to get the idea of it, because people like understand that, okay, you get an image, you process the image, you like extract some information from it, you segment it. But the idea that you take sensor data and you form an image seems a little more abstract to people. But in fact, that's how everything goes. I don't have my cell phone with me because I forgot it, but you know, people think that the sensor in the cell phone just produces an image. It doesn't, okay? It produces data, and then the data from that sensor is converted into an image, okay? If you just looked at the thing that came out of the sensor, it would be garbage, okay? So there is no modern sensor that directly produces an image as a practical matter. Okay, maybe you could find something, but it's really hard, okay? Mostly all the sensors really produce data that gets turned into images, okay? So then you really have the joint optimization of the sensor design and the algorithm which forms the image. And the problem of forming an image is really an inverse problem. Basically, you have measurements, and from those measurements, you want to determine this unknown image, okay? So this course is really about solving the inverse problem. It's not really computational imaging, because computational imaging would be about the discussion of the sensors too. And I just feel like there's, it's not that that's not important, that's super important, but the problem is that it tends to be distributed across many fields, because every field has different sensors with different properties. There are some commonalities, but also I feel like this part of the problem deserves its own treatment. Okay? And frankly, it's part of the problem that often people are missing, because they may come from different fields that, where they have expertise in the sensor design and the information they're getting from the sensor, but what they don't really know that much about is the underlying theory. And the theory tends to be off-putting to people, I feel. So that's what this course is about. I'm going to talk about that in some more detail. And then this is the never-ending textbook that I've been working on for the beginning of time that will serve as the basis of the course. I'll talk about that in a minute. Course information. This is a handout. I mean, it really doesn't say much. The syllabus, I didn't even bother updating yet. Okay, notes. Okay, these are kind of some other notes, but really we mostly go by this essentially textbook. And then homeworks. Oh, what is homeworks? What it is that for each week, now this isn't a normal semester, but for each week, I assign the problems in one of the chapters to do. Now, because you're humans, most of you normal humans, I assume, that you you tend to be like earthworms. If you poke them, they tend to go in the other way, and humans are the same way. If you're having a miserable experience, you tend to recoil from it, right? So people will be, there has to be some incentive to do these problems, okay? Or you will tend not to want to do them because they're hard, okay? So what I usually used to do, and this is where the exams work out, is that I would tell you, okay, and this is why we still may have an exam, particularly a midterm, that I would tell you that all the exam problems for the midterm or the final are going to, or both, typically both, are going to be from the homework problems. So that forces you to actually do the problems. Because if you don't do them, and then the person sitting next to you does them, then what's going to end up happening is that you'll be at a disadvantage, okay? So then that provides a subliminal incentive for you to work the problems, okay? And but you can work together, and eventually I'll give out solutions, at least not all the problems, because I don't have solutions to all the problems, but the solutions I do have. But still, you should definitely try to work them yourself. And the first chapter is basically probability. A lot of what we're going to talk about is modeling, okay? So basically, this is essentially a guide to say, what you should be doing in terms of working the homework problems, okay? Are there any questions? There are laboratories here. I have these laboratories. I also want people to do this deep learning laboratory because deep learning has become so important in everything. It's an important tool in this area and of growing importance. Okay? So, by the way, you guys can hear me okay, right? I'm not like muffled because of the mask, right? Yeah, okay. So the way that the deep learning lab is based upon Jupyter notebooks that you run on Google Colaboratory, so that you don't have to have everything all set up. How many people here use Python like regularly or even semi-regularly? Okay, yeah. Well, Python is really important. I mean, we're using it in the laboratory, but I feel a little guilty because I feel like what I should do is really set up the labs so that you install, you know, the thing with Python is that it's easy to use but hard to install, in my opinion. Is how many people are there experienced Python users in here? Yeah, you look at. So do you disagree with my statement, or feel free to disagree with me? Okay.
I've never tried with Microsoft or anything Microsoft related. Installation is in general very tough.
Yeah.
But if you go on Ubuntu or even Mac OS, it's just a line terminal.
Yeah, you got to get. Like, maybe parts of my environment tends to be a little clunky because it's old, and I hate to change it because then I'll break everything. But the, you know, you have to, usually people install Anaconda because that way you have so you have to install Anaconda first, and there's a lot of sort of environment specific things that you have to configure first, and most of you may have a lot of that done already. I'm not going to show you how to do it, but the point is that it's worth taking the time to learn those kinds of things, and they change, you know. It pays off because it's becoming the tool of choice for doing a lot of this kind of research. You know, I think someone made the comment to me that Python really is the programming language of data science, you know, and I think maybe that's true. It's certainly the programming language of deep learning, and I guess maybe people in the statistics area would say that R is, but I feel R is kind of specialized. And the thing about Python that's very powerful is that it's designed to interface naturally to C. So Python sort of serves the role of MATLAB in that it's kind of easy to use. It's much better designed from a computer science point of view. But it interfaces much more efficiently to C. And in data science, a lot of your core computations need to be computationally efficient. So that's a real plus. But then these things here, some of these are written in C. So you actually have to do the stuff in C. And and I think they're pretty self-explanatory. I'll set up the schedule, okay? And there's one part, okay, yeah. So I'll set up the schedule. Oh, I guess I should update this Piazza thing, although this may not be super necessary. I'll set it up, but it may not, since the class is small. And oh, by the way, you can't respond to my emails, but I think I'll change that. It's a small class. It's I have as the instructor the option to make the email list so that you can reply or not, and the default is so you can't, because if you had like 100 people in the class, you wouldn't want everybody replying. It would kind of be chaotic. So, but I couldn't change it because it seemed like the Purdue's network was not running very well today. Okay, so class notes. So I'm just trying to think. Okay, so save as desktop. Yes. This thing asks you to do this over and over again, and I don't really understand why. But okay, so so this is the table of contents. So we'll go through this. So we're going to first start off with talking about probability and estimation, and then we'll get into image models, okay? Causal models, non-causal models, and then how you use those models to do solve simple inverse problems. But we'll find out that this course is, like I said, it's not really a computational image course per se, because in computational imaging, the key issue is what we're going to call the forward model, okay? It's the model of the sensor, okay? But here, in this class, our model for the sensor is usually going to be very simple, okay? Sort of generic and simple, okay? And we're really going to focus on solving the inverse problem. And the inverse problem, the key model is not so much the forward model. I mean, the key model in terms of the technical innovation is not so much the forward model often, it's the prior model. The prior model is sort of the tricky thing. So the prior model is the model of the image. So you're basically modeling the sensor and the image. And an accurate model of the image is it's going to turn out as very powerful. So a lot of this course is about how you model the image. And we start off with very simple, ineffective models. Okay? And then we evolve to much more sophisticated, much more effective models, and that's where things like deep learning comes in, because you can use things like deep learning as a model. Okay? Now, and by the way, machine learning problems are inverse problems usually. Okay? I mean, they're almost always inverse problems. Okay? So you have some sort of observation, you want to infer something. So you could sort of either say, machine learning is a sub-branch of computational imaging, or you could say that computational imaging is sort of a sub-branch of machine learning. I don't know. Probably neither is true. But the techniques are very similar. It's just that maybe the goals are a little different. In the case of computational imaging, you're trying to form an image, okay? And in machine learning, you're usually trying to infer some kind of unknown quantity that has some kind of inference, a value in an inference problem, right? So, okay, so we're going to talk, and then along the way we're going to learn about things like, okay, we're going to talk about non-Gaussian models, and then we're going to learn about a lot of different optimization methods, but in the context of solving problems, which I think is often good, because then you see how they're used as opposed to just using them in a completely abstract way. So, like, there's this thing called majorization that comes up all the time. It's really handy, and once you get the hang of it, you'll want to apply it to everything. Okay, and then we'll talk about constrained optimization is super cool. Constraint, and it's very hot these days. It's counterintuitive as to why it's valuable. And then this is something I'm particularly interested in. The 10, I threw it in there. We'll go over that. Those are plug-and-play methods, or methods for integrating basically heterogeneous kinds of models, so deep learning models with sensor models. And then we'll talk about expectation maximization, which is super important. How many people have heard of expectation maximization? Okay, so, and a lot of people use it without understanding what it is. I mean, there's some value in being able to do something without understanding it, but if you have a kind of theoretical understanding of what it's doing, it's a lot more useful. We'll talk about hidden Markov models and Markov chains, and stochastic simulation. That's things like simulated annealing, if you've heard of that, or Monte Carlo Markov chain methods. And then we'll do that maybe somewhat in the context of tomography. Okay, so I think blank. Oh, yeah. So I should have printed this out. Oh, let me see. Bright. I thought they said I had to bring my own chalk. There's a lot of crazy stuff they said that wasn't so true. Make a change with, I don't know what this means. Okay. So, any questions? Okay, so what's the problem? So you have an imaging system. So the idea is that you have something you want to know, X. This is an unknown image. And you measure some data, Y, okay? And often, in addition, there's some kind of thing in here that you don't know. I'll call it phi, okay? And phi is like, I want to make sure my notation right. Phi is like some unknown parameters of the system, okay? So this is the imaging sensor. Okay? And so for example, this could be like an electron microscope, where Y is the data that comes out of the microscope, X is the unknown sample which you'd like to probe. There's a whole issue of how you specify X. Like, what is X? You know, in a lot of imaging modalities, particularly early imaging modalities, they tend to be what you call qualitative. You just look at it and you go, oh, it's a picture. But it doesn't really mean anything. It doesn't represent any physical quantity specifically. It's just like, it's like when you take a photograph and you just say, oh, you know, it looks nice, but it's not quantitatively accurate. Ideally, X here, the X is might be an image or it might be a volume. So if it's an image, it's a discrete array. It's a vector array of values that represent pixel values. If it's a volume, then the elements represent voxel values, okay? And it can be actually 4D in time. Sometimes I like to call that a toxel, okay? I don't know, I just made that up. So then and these each voxel represents some quantity, like it might be density in grams per cc, or it might be X-ray density in terms of inverse centimeters, so attenuation rate, or it might be, I don't know, whatever physical unit you're trying to measure. And then you have some sort of sensor that measures data, okay? Now, I like to say that, you know, signal processing is supposed to be 1D, and then image processing is supposed to be 2 and more D. But everything's image processing, because you know, nothing, I mean, you hardly ever, because if you measure something and it's 1D, the first thing you do is you go, oh, let's make it better and we'll measure something else, okay? In other words, you know, there's just this natural trend towards measuring more dimensions, right? Like even in communications problems, which seem like they have to be 1D because it has to be in time, they have MIMO, okay? So they'll have multiple antennas they measure as a function of time, so it ends up being 2D, or you have like an antenna array, okay? So it's almost like, I like to think of signal processing as one-dimensional image processing, okay? So everything's image processing. Technically, okay, depending on how you want to define it, an image is usually, in its strictest sense, refers to something that you look at. Although, you know, you can call that a picture. So, but more generally, it can be any multidimensional quantity, and then you have to visualize it later. Okay, so what I'm really saying is this is a very general framework. Okay, there's all kinds of stuff you might want to infer, and then you make that inference from the measurements. So this might be like properties of the instrument. So if it's like an electron microscope, there might be parameters associated with the focus. It might be the tilt angle, the sample, or the positioning, or something like that, which maybe you don't know, okay? So these are sort of unknown parameters. There's a subtle distinction between X and phi that you can't rigorously define, but that you sort of know it when you see it, right? The phi is usually something you're not directly interested in. It's what's often called a nuisance parameter, because it's something you need to know, but isn't really your primary interest, okay? This X is your primary interest, but the problem is you can't really measure X effectively. You can't reconstruct it unless you know phi. You can't reconstruct the image unless you know the focus of the microscope. So then the problem is that, you know, this is not satisfactory because Y is in itself kind of useless. So what ends up happening is you put this into another box, which I guess I call inversion. And you form X hat. So that's your estimate of X. So can you see? Yeah, okay. So this is the estimate of X. And you may also, along the way, have to estimate phi. So this is the thing we're really going to focus on. How do you solve this inverse problem? I would argue that any sensor requires this. So even if you have a voltmeter, you go, oh, well, the voltmeter doesn't directly measure voltage. It measures something, and then you have to convert that to voltage, okay? The conversion is sometimes referred to as calibration, okay? Okay? So, but it's, you never, as physical scientists tend to think of this as they directly measure the thing that they want. But really, from an information processing point of view, you never measure the thing you want. You measure something related to the thing you want, and you try to guess at the thing you want from it, okay? And then there's, so that's a very different way of thinking about the problem, okay? And so then your goal is to try to make, you know, honestly, I think maybe it might be a little easier in some ways, harder in others actually, to think about this now that you guys have probably been exposed to a lot. I assume that you guys have all been exposed to a lot of deep learning stuff, more or less? No? Yes, no? Maybe so? Okay. It's hard for me to know because in the worlds I travel, that's like all that anybody does, okay? Okay? So, but I think in any case, a lot of students are getting very exposed to that. So they have this concept of a loss function, right? In deep learning. So that's kind of nice because at least got that sort of drilled into people's brains. So you have this like loss function. So the loss function here is something like, might be something like x minus x hat squared, mean square error. And then you want to minimize this. You want to minimize the expected squared error, say, or something like that. That may not be appropriate because it might be discrete, okay? But in any case, so that's the name of the game. And then, well, okay, then what happens is what happens in computational imaging, and what I sometimes call integrated imaging, is that you try to jointly optimize the imaging sensor design and this inversion. So here's where the clever thing comes in. That's kind of really makes this quite different. Is that people tend to think of this as, oh, well, you create an image and you just kind of clean it up. Okay? No, what you might collect here could be very different than an image. Okay, and then you try to put it back together. So I like to call this. I got this name from Professor Bell, if you know who he is, okay? And so I really have to give him credit, because he was the one who invented this theorem. It's called Mick-Jaggard's theorem, okay? So Mick-Jaggard's theorem is, you can't always get what you want, but if you try sometimes, you get what you need, okay? So the idea is this. Well, you can't measure x directly. But so then you measure what you can measure. And so every real engineering problem, every real problem always involves cost, okay? You can never have infinite cost. Right? So what you do is you measure the most informative data at the minimum cost. And you then use the data that you can get to put together the reconstruction. So as computation gets cheaper here, then it dramatically changes your strategies towards doing this. Because it says, okay, physicists are trained to say, let's build the perfect instrument that makes the perfect measurement with no noise in it, and it's pristine with zero distortion, okay? But the cost of that is like infinite asymptotically. So instead what you do is you say, okay, I'll be willing to accept less pristine. I'm going to lower my standards and take what I can get over here. It might be noisy, it might be distorted, it might be sparse. And then I'll use this computation to put it back together again, okay? And that leads to dramatically different outcomes in terms of how you design sensors. And that's why it's interesting, but you need to understand this first. Now, traditional inversion methods just require, you write down some equations, you try to invert the equations, okay? So like the traditional inverse problem is that y equals ax, right? And then what you do is you say x hat equals a inverse y. The problem with this is manyfold, okay? First of all, A may not be invertible, right? There's a number of reasons A may not be invertible. First of all, A may not be square. If it's not square, it could have, okay, the other thing happens is this, when you have some noise, okay? So what may happen is that Y may not be in the range of A, okay? Because of the noise. So if the range of A is not full, right? So if A is shaped like this, right? Then its range, then in this case, this is M by N. I use M usually for the number of outputs and N for the number of pixels, okay? So in this case, what may happen is that Y may not be in the range of A, okay? So in that case, you can't invert it, okay? So there's no solution in that case. You can't find it, okay? So, and then the other possibilities you might have like this, M, so that may not be the case, okay? The other possibility is that in that case, it could be that the null space, the null space of A we'll call it I'm looking for a fancy N. Is that a fancy N? We'll make it like that. I don't know. That's the null space, okay? So then, and there's an infinite number of solutions. So you can have no solutions. Solution doesn't exist. You can have an infinite number of solutions. And then you can have the case where it's unstable, okay? So if you have the A here equals, I always forget, is it U sigma V transpose, okay? Where this is, these are the singular values, and it could be that sigma equals diagonal sigma 0 through sigma, I don't know, I'll call it P, like that, being a little fuzzy because I don't want to be too precise because I'll say something that's wrong. So that, and it could be here that the ratio of sigma max, and we'll make it like this, sigma I is greater than or equal to sigma I plus 1. So they're in decreasing order. And then we have that sigma 0 over sigma P is equal to conditioning number. Okay, and that could be much, much greater than 1. It could be like 10 to the, I don't know, 10 to the 9 or something like that. Let's just say, actually a pretty practical case could be 10 to the 6, okay? So then, well, yeah, mathematically I can invert it, but it's a practical matter. If I try to invert that matrix, some of the singular values are so small, it's like trying to unfilter a signal, okay? If you had a signal and you filtered with a low-pass filter, in theory, you can just, the low-pass filter is never perfect, so you can always take the filter whose frequency response is the inverse and just bring it all back, and it's fine. You just take those little signals, you multiply them by 10 to the 8th, and then they're fine again, except for guess what? When you take a signal and you multiply it by 10 to the 8th, you're going to just take any little tiny bit of noise and you're going to get this huge signal, okay? It's like saying, I'm going to listen to somebody speaking on the other side of campus. I'm going to just amplify their voice. Well, I guess there's some amount of the molecules are vibrating a little bit, but there's so much noise, thermal noise, I could never pick it up as a practical matter. So there's 3 failure modes. I'm out of time. There's 3 failure modes. Two is inversion. One is doesn't exist. the other one is not unique. And the third one is unstable. Okay, so these same three failures occur when you're trying to solve these problems. And usually, this is, and more, this is the case that happens the most. Because it's expensive to collect lots of data. So instead what you do is collect a little bit of data. This is what machine learning's all about, right? Machine learning, you like make some measurements, you know, and then you come back and you say, I think Colonel Mustard killed whatever in the dining room with the candlestick, okay? That's the game of Clue, just in case you've never heard of it. I wasn't threatening anybody that day. There's a board game, okay, where you play this, okay? Where you can make these wild inferences and they go, wow, how did you know that? Have you ever played this game? It used to be popular. I have it somewhere, maybe, somewhere, where it's like there's 20 questions. Okay, and it's just miraculous. You think of some crazy thing, you answer these questions, and it comes back and it says, coffee cup. And you're like, how did you know that I mean, obviously it's not a person, it's just a machine. But machine learning can make wild inferences that are pretty accurate. Why? Because statistically, people don't just think of anything, okay? Okay, it's like I once took this little thingy, and he went at the end, he said, what are you thinking of? I said a red hammer, and they go, and you scroll down, it says red hammer. You go, how do you know that? Because most people think of red hammers when you ask them this question, okay? So Bayesian statistics, okay, the prior distribution, that's what makes machine learning tick, okay? And this is what we're doing here. It's essentially like a machine learning technique that you're kind of guessing what the reconstruction is from the data you have available, okay? And it's amazingly how accurately you can do that. So you jointly design the imaging system to measure the things that are most important along with the reconstruction. Now, to do this reconstruction, this is what this course is all going to be about in one way or the other, okay? And it turns out that the methods for solving a problem like this, particularly when the data is sparse like this, okay, are not intuitive, okay? That the way you go about doing it is quite different than you might imagine, okay? And I'm going to just draw it really fast because it's very important. What happens is this. You take the data, okay, and you say, okay, you have the image X. The image X, what you do is you build what I'll call a forward model. We won't spend a lot of time on this in this class because we'll just assume some simple forward model. It usually be something like y equals ax plus w, okay? It can be more complicated in a real problem, but we'll do something like this. And then what happens is that then you take the real data and you compare. You compare the actual measured data this is your guess at what the reconstruction is based upon your mathematical forward model. And then you compare them. So this is, and you say, okay, if they're not the same, you feed it back. This is like become the classic way of solving inverse problems. Now the other little thing here, which honestly people complain that maybe this isn't symbolically the best way to draw it, but we'll go with it, is that you put a thing here called a prior model. Okay? So the idea here is that first of all, it's a naturally iterative process. Because it's like solving a puzzle. You have a mathematical forward model, you try to find an input to the forward model that produces the output that you've actually observed. But the problem is the output is noisy, and probably there's not enough data to actually solve the problem. Because this is sparse measurements, So there's an infinite number of solutions that could fit it. So among all those solutions that could potentially fit it, or approximately fit it because it's noisy, you want to pick one which looks reasonable. That's where machine learning shines, right? So that's the so-called prior model, okay? So you want to balance two things. One is to fit the data and also be reasonable, okay? So the class is spent a lot of time talking about prior models because this is a crucial piece. We spend less time talking about forward models, and we spend a lot of time talking about how to solve an optimization problem like this and the various tools one can use. And that's where things like the EM algorithm comes in, coordinates net optimization, constraint optimization, all these different optimization techniques, majorization, are how you solve these optimization problems. But one last thought I just want to say is that this is very unintuitive because when you're solving an inverse problem, your natural tendency, and you don't even realize this, but it's going to happen when you go to do it, okay, is your natural tendency is to want to go in the other direction, to take the data and produce the reconstruction. But here, you solve it by going in the wrong direction. So it's actually, and that's where I think the most important thing you'll learn in this class, the sort of the philosophy of how to solve the problems. All right?